Hello everyone, my name is Elizabeth. I'm doing my presentation on evolution complexity, which revolves around the increasing trend of complexity over the history of life. Well, one way to examine evolution trend and complexity is to define what it is. There has been a lot of debates about the good way of determining the meaning of organal complexity. There's actually one simple measure for comparing the complexity of different organisms, which is the number of different cell types typically found in the body of an individual or of a particular species. Examples include humans, jellyfish, and insects. Humans contain several hundred different types of cells that perform different roles, like red blood cells carry oxygen around the body, spindle neurons transmit electrical signals across the parts of the brain, and specialized olfactory sensory cells in the lining of the nose. Jellyfish typically have less than a dozen different types of cells, though one of these is a familial stinging. Note this. And insects tend to have around a quarter of many cell types as males. Well, as you see, not all the males have the same cell types as humans. Well, as we see in figure 3.11, it shows a plot of the age of the first appearance of a lineage in the fossil record against the number of different kinds of cells typical for that taxon. There appears to be a clear upward trend as time goes on. Animals with more and more different types of cells appear. Evolution seems to be driving towards a more complex animal life. As we see in the lower part of the graph, uh, are not past forms, but they've been replaced by better models, and they do represent complementary species. Well, Pasteria, which are spongy, and Syria jellyfish are not just ancestors; they're just re- uh, relatives. Okay, the reason for evolution going towards more animal complex life is animals have some kind of evolution advantage over the simpler relatives. Well, we heard in chapter 2, it talks about being in the earliest steps of the evolution of life in terms of any forms that could reproduce more efficiently, that could have been displaced less efficient forms in which it promotes the evolution of more complex replicators with enzymes, cell walls, and so on. And the animals with few cell types have not been more complex animals. There's no obvious trend in evolutionary success when speaking of the number of species that are alive today, and complexity as measured by different cell types. As we see in figure 3.12, it shows the plot of the number of different cell types against the number of species that are found out get a different picture. Well, we see in the points of the graph in that same figure, they represent different levels of taxonomic hierarchy. Porphyria, Syngria, and Caesar are Coperia and Ecodema, a phyla, which is the largest subdivision in the animal kingdom. Phyla generally represent over half a billion years of evolution, so it's surprising that some of them have accumulated more species than the class Aves, birds, which had less than 100 million years to keep species, and the family Hominidae, which is only around 20 million years old. And some of the data points are nested with the others. For example, birds, aves, are one of the lineages within the Taphiria, which contains birds, lizards, snakes, and crocodiles. which in other words, some of the members of that theory have more cell types than others. So it doesn't seem very fair, a very fair comparison as to the graph shown in figure 3.11. Okay, the pattern of diversion. Well, the always animal forms was very simple. More complex forms evolved over time, but simpler forms didn't disappear. Many lineages spread out in complex space, just like as horses in ecological space. And while that pattern of evolution looks more like an undirected search of space and possible forms, well, Stephen Jay Gould refers to the pattern of division as diffusion from the left wall, which is a reference to the drunkard's walk analogy, which is a simple thought experiment which demonstrates how an undirected process can end with an unpredictable outcome, as it's seen in figure 3.13. It shows the same figure from 3. The same figure from 3.11, but it's drawn in hexagonally to show this more or less more as a pattern diversion than a lineage. Well, comparing the drunkard's walk analogy to the evolution of complexity, well, unlike the drunk in the field, the complexity cannot go as far in any direction. That means that there's a lower bound of complexity of one cell type. A cellular life that has zero types, nor can have negative values. Well, like the drunk in the alley, the light starts at the left wall in a cellular life, and the only way to stay the same or increase, which is increase the number of cell types over time. So more and more cell types evolve over time. While the upper limit on complexity was unclear about either biological complexity has an upper limit like a zoning boundary of the gutter, or keeps on going up and up. And one way to look at the upper limit of complexity is that it's been empirically defined by the evolution of major innovations in the way that organisms are put together. Well, an example of this is the suggestion of the evolution of eukaryotic cells via the merge of previously independently evolving lineages that may have opened up new evolutionary possibilities that allows the development of multicellular organisms with many different cell types. Well, if the eukaryotic cells didn't evolve, then the upper limit of complexity might have remained as single cells with relatively small genomes. Major transition in evolution, like the origin of the eukaryotic cell and the subsequent evolution of multicellular, may allow evolution to hop over the white wall and increase complexity. And I linked a video that shows a model of these being used to show how the eukaryotic cells have evolved over time, and it will result in a directional trend in the maximum complexity, with each transition pushing the upper limit to the starting point. It will keep pushing the upper limit of complexity, and it will eventually break that barrier. And thank you so much for watching.